We often would like to find probabilities of different types of combinations of events, okay? So we don't normally just look at one single type of event. And so the way that we do these, it depends on the relationship among the events. So one of the relationships are events that we call mutually exclusive events. If two events are mutually exclusive, that means that they have no outcomes in common. In other words, there's no way that both events will be occurring at the same time. So one of the probabilities that we're going to compute is going to depend on that relationship. Okay, if we have two events and we don't know if they're mutually exclusive or not, okay, or in other words, if they could potentially occur both at the same time, then the probability of E union F, or in other words, the probability of E or F, so the probability that one or the other occurs, is the probability of E plus the probability of F. And then we subtract off the probability that they occur at the same time, which is E intersect F, or in other words, this symbol right here you can think of as the word AND. I'm going to draw a little picture so that we can kind of see this, and often we'll think of probabilities in terms of Venn diagrams like this here, because it helps us kind of understand the rules. So we think of the event E, okay, everything in this circle would be the event E occurring. And we could look at the event F, could be everything in this circle. And then we can think of the probabilities as the areas of these. So the probability of E we could think of as this just area of this region here. And the probability of F we could think of as the area of this here. So when we're talking about the probability of E or F, meaning we just want to know what's the probability that we end up in one of these circles. If I add those two probabilities, you can see that I've double counted this intersection of those two regions. And so you add those two, but then you've double counted it, so you need to get rid of one of those counts. And that's where this formula comes from. Now, if E and F are mutually exclusive, that means that they do not intersect, which means you didn't double count any intersection at all, and in fact, this intersection is just zero. It can't even happen. So our probability becomes a little bit simpler. It's simply the probability of E plus the probability of F. You draw one card at random, that should say at random, from a standard deck of 52 playing cards. What is the probability that the card is either a heart or a face card? So, our two events here, probability is drawing a heart, and event F would be the drawing a face card. Okay. And so we're looking for the probability of E or F, which is the union E or F. The probability of E or F is the definition of, is the probability of E plus the probability of F minus the probability of E and F, or the intersection. So now we just go through and do each of these probabilities. The probability of drawing a heart. Well, there are 13 hearts in the entire deck of 52 cards. So it's 13 out of 52. Plus the probability of drawing a face card. Well, there are 3 face cards in each suit, and there are 4 suits. So there's 12 total face cards. So 12 out of the 52 cards. And then minus, now we look at what's the probability that the card I draw satisfies both. What's the probability that both it's a heart and a face card? Well, there are only 3 face cards that are hearts, or 3 hearts that are face cards. The Jack of Hearts, the Queen of Hearts, and the King of Hearts. So this is 3 out of 52. So now we just combine these, and they all have the same denominator, so we just add 13 plus 12 minus 3, and that's 22 out of 52. Of course, that reduces to 11 out of 26.